Okay, now we're looking at this problem. This is like a curved wall, and we don't have to worry about the horizontal. There's just atmospheric pressure on the horizontal. Uh, and we just have to worry about the weight of the water in this section right here. The wall, 5 meters long, 1 meter wide, and it's a parabola. So you can take it as the depth equals 5 times the horizontal distance squared. And if I take this as the origin, I can go from right to left, or I can flip my diagram around. That might make it easier for your integrations and your thinking and stuff like that. Okay, this is 1/3 of the way up. This is a triangle, so we know the centroid of a triangle. We find the centroid of the force just like the centroid of an area. It's 1/3 of the way up, which would be at 1 meter, 1 meter up. And it's 5 meters long. It's 3 meters down. So I have to revise my formula, the parabola. So the z depth, z, and we'll go this way in x, and flip mirror image the diagram if that helps you. The answer is going to be the same. So the depth is going to equal 3 times x squared. Because when x is 1 meter, when x is 0, z is 0. When x is 1 meter, z is 3 meters. This will be 1 meter. 1/3, just like all the other triangles we've done. 1/2 base times the height. Here's the base, 3 meters. 1/2 base times the height. Let's go take a look at what they say. So this calculates the pressure and our load curve now. That's the 150.1 kilonewtons per meter. 1/2 base times height. That's the 225.1 kilonewtons. Now we got to find the area of the water. For parabolic area is 1/3 AB. Now, let's see. Do I have that in the book anywhere? I think you'd have to go look it up. I'm looking in the back of the book right now for parabolic area, and I don't find it. Oh, here we go. Parabolic area. Yep, 1/3 AB. 1/3 base times the height. So it is in the back of your book. Oops, there we go. And that is the area of interest. So rho GB, rho G, density times acceleration due to gravity times volume. B times the area is that. B is 5 meters. Area is this, density, acceleration due to gravity. So that's the force of the water. Resultant force is, we got to sum the two. Did we figure out the, yeah, 1/2 base, 3 meters times the height, 150.1 kilonewtons per meter. So total force acting at 1 meter high. Okay. And the weight acting at, well, you'll get a magnitude by using the Pythagorean theorem. That's what this is all about. Total force acting on the wall. You won't get the vector direction. You could get the vector direction. Don't have to worry about it. Now, this is a varying area, and so this is the situation where the area, the dA, the width is going to be changing. The force, the pressure is rho gz. Might as well write that down. Pressure equals rho g z, and the now we're going to have to get the total force is, we're going to have to integrate over the whole thing. So the force is going to be the integral from z equals 0 to 1, pressure, rho g z, dA. dA. Now, this is what we need to figure out down here at z. dA is going to be going from, now z is the depth down. Okay, so it's just the width. dA is going to be the width times dz. It's just figuring out the width. It's going to be interesting. So it looks like z goes from 0 to 1 as it goes from 0 to 1. So width looks like it's going to be 1 minus z. When z equals 0, width is 1. When z equals 1, width is 0. Okay. And that is dA. Rho and g I can bring out front, since they're not changing. 1 minus z dA, dz is over here. This is the dA portion. I'm leaving a space between just to put in z. So our integral is from 0 to 1, so it'd be just 1/2 for z. The integral z dz is this, minus 1/3. That's equal to 1/6. And that'd be in, yeah, that'd be in the proper units. Okay. Rho g over 6. Okay, let's see what the book says. Did I do that right? Oh, there's 0.5 meters, 1 minus z. Let's see how they figured this out. So as you go down in depth, the equation of the line AB is, okay, x is this. So that's the x displacement. Here's the x-axis here. they're looking for the equation of this line. That's how the book does it. DF, there. I went the total width, by the way. I went by the total width. So I was finding dx. I mean, I was finding 2x, actually. So this is the total width, dz. And they did the number crunching, so zx dz. X is that. The 2 is already factored into here. Let's see. Yeah, that's right. So if you looked at the equations I did, I just calculated rho g. I didn't calculate 2 rho g. This is 2 rho g right here. Zx dz. X, then they're measuring it from the center, from the middle. That's the difference between the way I did it and the way they're doing it. So you get total force is just this expression. Figure it out. 1.64 kilonewtons. Z minus Z squared. Let's see. Here's yeah, Z minus Z squared, 1/2 minus 1/3. Yeah. Okay. I didn't crunch the numbers, but we got this answer earlier. Little different approach, but still the same. Now, we got to get the centroid. To get the centroid of the whole thing, we have to take the centroid of this. Well, we've already figured this one out, right? Where is it? PDA is this. Now we got to take Z times PDA. So it'd be Z squared x dz. And x is this, remember? Okay. Z squared, there's the 2 squared, x dz. This is the 2 rho g. Okay, that. And 1635 is what we should have gotten previously. There it is. Wait a minute. Come on. Total force. 1635 newtons. What we got previously. So Z is a 1/2 meter. Does that make sense? Yeah, it does, because we're going 3 meters down. It's saying it's only this far down, but the biggest area is way up here. It's not 1/3 of the way down. It'd be if this was a constant width, it would be 2/3 of the way down. It's turning out to be, if it's a 1/2 meter. Oops. There we go. Oh, there's a 1/2 meter. The width at the top makes the most difference of why that would be where the centroid is. I'm kind of surprised. Oh, wait a minute. 1/2 meter doesn't surprise me now. I forgot. I was thinking it was 3 meters deep. It's only 1 meter deep. So this does sound a little more reasonable now, because the pressure increases with depth, but the width is decreasing. So 1/2 meter. Okay. Okay. Now, I think what happened was, yeah, I had an extra blank slide at the end. So this is the end, a little bit longer video this time, but the end of the center of mass videos. So we can call it a night, a lecture, and you guys can get to crunching on homework and all that stuff.